Director. And this afternoon, we are fortunate to have Dr. Almost Doctor, he's a doctoral candidate, Mr. Chang Ping, who is a PhD candidate at the Freedom Systems Center here at North Carolina State University. He is under the direction of Drs. Alex Wong and Iqbal Hussain. He has 7 years of research and development experience on protection and control of DC and AC systems, especially on emerging power switching technologies and interconnected DC grid system. So welcome. Thank you for doing our presentation this afternoon. So we'll go ahead and get started.
Okay. Hello, everyone. This is Chang Peng. So today, I'm really glad that a lot of people are interested in this topic. And today I'm going to talk about the 1 millisecond mechanical switch our center has developed in the past 2 or 3 years. And I believe that this is a very important device for the protection and the control in medium voltage and high voltage DC and AC systems. I am a PhD student at the Freedom Center at North Carolina State University. My advisors are Dr. Alex Wong and Dr. Iqbal Hussain. So first, I would like to talk a little about why do we need DC circuit breakers? Why do we need this really fast mechanical switches? There have been very bold plans all over the world, and they are seeking possibilities to build a DC grid, a high voltage DC transmission backbone system. The main purpose is actually to integrate more renewable energies. So as you can see here, there are a few plans. On the left is something happening in Europe. This plan is called Super Grid. It has been proposed for maybe almost 10 years now. People are still working on it. And there are even larger plans which interconnect the Europe and the Africa, because, you know, Africa has a lot of solar energies, and it would be really nice to have those interconnected and transmit the power to where they are needed. So this is called, I'm not sure how to pronounce it. It sounds like a desert tech. Okay, and there are more. Those are not happening yet. Those are in planning, but something has been going on in China. There are a few multi-terminal DC systems in China already in operation. So one is called the Zhoushan 5-terminal HVDC system. One is called the Nan'ao multi-terminal system. They are all like a radial topology-based multi-terminal HVDC system. And also in the United States, there is also something very similar. There is something called Atlantic Wind Connection. It interconnects a few northeastern states in America. Those all have large abundance of the offshore renewable wind energies. So they would like to integrate those wind energies through HVDC grid to the onshore load centers. So one example here is in New Jersey. Actually, this is the first phase for this project, the New Jersey link. Well, it is reasonable for them to do this because New Jersey has very few power generation, but it has very large load centers. And because of the transmission congestion, I mean, in terms of power transmission, because of the congestion, the price over there is a little bit higher. Actually, it's the fifth or the fourth highest electricity price in United States. So they hope that this kind of HVDC connection can help them to integrate the offshore wind energies for them to reduce, to lower the electricity price. Okay, I have shown a few DC grid plans, but why do we need it? A few years ago, we had conducted some internal study, and we also have publications on transactions regarding what kind of What kind of DC system do we need? How does the DC system will actually improve the system performance? Can increase the power efficiency? Can reduce the load? Can reduce the cost? So in terms of offshore energy, it will be always like this. The basic topology will be like this. This will be the wind or any renewable energy farm, a lot of generators over there, and you need to collect this energy to put them into a centralized converter station or any substation, and they transmit the power to the load centers or to the main grid. You have a lot of ways to do this. Right now, almost all the wind farms offshore wind farms are integrated like this. So in the offshore wind farm, they are, first of all, the generations are AC generators, and so you need to interface them with converters. There'll be AC/DC and then DC/AC conversion because you need to connect them to an AC grid. And then usually it's at a 33 kilovolts DC AC system, and then you collect them all to offshore substation. Typically it's 132 kilovolt HVAC, and then you transmit them through HVAC cable, underground cable, undersea cable to the ground. So that's usually how people do it. But recently, I mean, in the past about 5 years, in Europe, some companies, some utilities are doing it differently. They would like to replace that HVAC cable by these HVDC cables. There are a lot of technical reasons behind, but there are also economic motivations behind. However, we would like to make it even more DC. We would hope that we would use the HVDC for transmission, but we also would like to use the DC for collection, for distribution, and we hope that this can reduce the energy loss even further. We did an evaluation of these 3 topologies. So, and we are very, very conservative about the DC system. We try to, for example, here, as you can see, we have an AC/DC conversion stage here, and we also have a DC/DC conversion here. Sometimes you can eliminate this power stage. In that case, you will need less equipment. You will have more. You have higher efficiency. But we are trying to be conservative about this DC system, and even being very conservative, we have results like this. This graph here shows the cost. I have somehow collected a lot of data on this on the cost of this equipment used. So as you can see, a lot of cost goes to the cable. That's I mean, people say, oh, power electronics seems to be very expensive thing, but consider the cable. They are basically copper, a lot of copper, and a lot of insulating materials. So AC cables have their problems when it comes to a long-distance transmission, mainly because of the reactive power. A lot of reactive power is flowing in the AC cable, which does not actually contribute to the power transmission, but it occupies the available transmission capability of that cable. So, for example, you have a cable maybe this big, but you're actually using a portion of it. So that's a waste of copper, you know. Okay, so but DC system has no problem like this. So okay, that's one of the biggest reason that DC long distance underground or undersea transmission makes sense. On the other hand, if we look at the loss, we will also notice that the DC system here has less loss. But potentially, we believe that by better design of the converters, by better design of the system, we can achieve 15% more cost reduction and 1% more loss reduction. Okay, with that being said, like high voltage things, let's talk about microgrids, because this may be more like close to us. is more likely to be built everywhere. DC microgrid is envisioned to integrate the loads, the distributed generation, renewable energies. So people are comparing these two topologies. Very simple to see that if you use a DC transmission, if you use a DC microgrid, you get rid of a lot of power conversion stages. So that directly results a better efficiency and also low cost. So I'm not going into detail of those, but let's look at the DC. Let's see. Okay, we summarize that the benefit of the voltage source based DC grid has the high efficiency, high flexibility, and the stability in terms of power system and power quality, and the reduce the cost and the components, and also the reliability. But let's see what's the challenge. The challenge here is control and protection. So the control here does not actually mean like a control algorithm. It's a more like it's a broader term to to optimize the best operation for the system. So control can mean the stability control. It can also mean the power flow. I would like to switch off this line, switch this area of load, and I would like to guide the power fly to another path. So that's also control. And if you want to do that, or if you want to do protection, you want to isolate a faulted area, a faulted line, you would need DC circuit breakers. And that's what's missing today. Okay, then before we talk about DC circuit breakers, I'm pretty sure some of you are not very familiar with AC circuit breakers, so let's have a very brief review of AC circuit interruptions. Here I did a simulation. We have a transmission line here, and we assume that a fault happens here. So this B1 is a circuit breaker. And what happens if there's a fault? This is a three-phase system, and we have assumed a phase-to-phase circuit in here. And if we look at the sequence here, at this moment, the fault happens. At this moment, somehow the relay detects the fault and sends out a trip signal. And at this moment, the contact of that circuit breaker actually opens. So there have been a few delays here. And this all, they should all be counted into the total time for you to interrupt a fault. We have assumed a 230 kilovolt system, but when we look at the total interruption time, we need to keep in mind that a mechanical device, which is to open and to isolate the two electrical systems. So what happens over there? If you assume that this circuit breaker is a set of contacts, two mechanical parts that will open at a moment trying to isolate the two electric systems, because once they open and once it actually isolates this part and that part, the left part and the right part actually become two electric systems. And the voltage at this terminal and this terminal are decided by each of those two electric systems. So the problem will be there will be a huge voltage across these two contacts. That's what happens in an AC interruption. Well, ideally you hope that, okay, I open this contact, the circuit is interrupted, nothing happens, that's all. But that's not the case. What really happens there is, if we look at this sequence, this moment is the actual opening moment for the contact to initially part. So at that moment, there's a very finite opening between the contacts. And what happens then is there will be an arc. The current will trying to flow if you are not strong enough to actually break the circuit. So the arc will continue flowing until some conditions are met. And this conditions is, well, in terms of arc, it is there will be no current, and at that moment there will be no arc. For a very short period of time, there's no arc, And at the time, if you have the capability to withstand the voltage to recover the dielectric strength at that moment, you'll be able to interrupt the circuit. But if you are not, then the current will continue flowing, and you are not able to interrupt the circuit. That's what happens here. But in terms of total interruption time, in terms of this, because we care about how long does it take to interrupt this circuit. The first thing to do is you send out that trip signal. That signal comes into the circuit breaker. It takes 20 to 40 milliseconds to actually open the contact. And after that, you still need some time to try to extinguish that arc. You have to wait for current zero. And if the first current zero, at that moment you did not actually interrupt the circuit, you will wait for another one. So the arcing time typically is in the range of 20 to 60 milliseconds, and then the total will be 40 to 100 milliseconds. That's a long time, but that's what's happening in AC systems. It's acceptable. Then let's look at the DC system. Okay, we talk about the condition needed to interrupt the circuit to extinguish an arc, and that is you will need a current zero. In DC system, you don't have this. And what happens is, okay, there's no natural current zero, and you need to create some. So you can create some artificial current zero. This is what I have done a few years ago before I joined here. I designed a DC transfer switch in China, April. I designed 130 kilovolts, 5,600 amp DC transfer switch for HVDC transmission. So what happens now is we use some alternating circuit to try to create a current zero. This alternating current, this circuit, has some very subtle interaction with the arc. The arc itself is very complex, but it has a tendency of instability. It has very strange VI characteristics. It's negative resistive. So when you put that to oscillating circuit, something happens like this. The current, the arc current will oscillate. It will oscillate, not only oscillate, it will be amplified. The oscillation is being amplified, and it goes up and down, up and down. So here is 5-something kiloamps, and you will oscillate, oscillate. Okay, at this moment, it oscillates, it comes to a current zero. Okay, you got it. Then the circuit is interrupted. The arc is extinguished, and mission completed. So let's look at how much time is needed for this. First of all, you still need to open the contact. That's the time before the initial contact opening. That takes 20 milliseconds. On the other hand, this is the arcing time. The arc is burning in the circuit breaker chamber. So that takes about 20 milliseconds. In total, that's 40 milliseconds. Okay, this is for DC transfer switch. It is used in HVDC transmission based on line commutated converters, not voltage commutated converters. So that's a different topology, and the purpose is also different. But we are talking about DC circuit breakers here. The requirements will be different. And why is that? Let's look at these three. This is a DC grid based on voltage source converters. I made a mistake here because this is apparently not a mesh system. This is a radio system, but never mind. Let's look at what happens if there's a fault in this voltage source-based DC grid. I have implemented a fault here. This is a simulation in PSCAD, by the way. It has all those voltage source converters, those switching functions in this model, so it should be very accurate. And it also has a transmission line model, so all these like transient should be very accurate. We have a 3-terminal system here, and some fault happens here. Then let's look at what's going on with the DC voltage. We are running this system at 400 kilovolt, and if there's a fault happens at 1 second, what happens after 40 milliseconds? we see that the voltage here, the voltage at these 3 DC terminals. I'm showing 3 DC terminal, the voltage at these terminals here. It drops to, well, it's not really 0, but it's 100 kilovolt. So that's really too long. At that voltage level, the system doesn't really work. So your whole system is down. And if you have like a more voltage source converters interconnecting in the system, a more complex DC system, gradually the whole system voltage will drop, and the system is down. The power transmission is interrupted. So 40 milliseconds is too long. Actually, in 5 milliseconds, if you look at here, 5 milliseconds, the voltage drop comes to about 50%, about here. That's in 5 milliseconds. So we are really talking about a few milliseconds here. You don't have that much time to protect your system.
Chang, could I ask a favor?
Yep.
Could I ask you to use your mouse to point with? That way the people online can see where you're pointing.
Okay. Oh, I see.
Thank you.
You cannot see the point here, the laser? No? Okay. All right. Okay. I was saying, yeah, at the 5 milliseconds, well, if you look at the simulation results here, 5 milliseconds, the system voltage dropped to about 200 kilovolt. That's 50%. So consider you are controlling your voltage source converter, and the voltage dropped to 50%. And I think it was very difficult to maintain the normal operation of your converters, especially consider that you are trying to transmit power from AC to DC. So, so the conclusion is we're talking about a few milliseconds. That's our target. There are a few ways to interrupt the DC circuit. As I mentioned, there can be mechanical DC circuit breakers. There can be solid state ones. I haven't talked much about that. But the solid state is you use the power semiconductors. There will be very high losses. So this loss is not that simple. It's loss in your system. You need cooling. That's extra cost. And you are actually stealing power from the transmission system. That's really a bad thing. So people come up with hybrid DC circuit breakers, in which they will use perhaps solid state component, perhaps a hybrid, perhaps a passive component, and they will also use a mechanical switch. And this mechanical switch is used for fast opening during the interruption process, and it is used to reduce the conduction loss during normal operation. There have been a few different patterns in the last 5 years. The topology may be different. You may have options for those for which topology you want to go with, but really you only have one option for the mechanical switch, and that is a fast mechanical switch. So that is why this topic is about this fast mechanical switch. But before that, maybe we wonder why do we need a fast mechanical switch? So let's look at how does a hybrid circuit breaker work. First, you have the current flowing into your mechanical switch, and then you want to transfer that switch to your semiconductor switch here, at this stage, and then you want to turn off your semiconductors so the current goes into the MOV. And at that moment, the voltage is really high. You turn off your semiconductor, that takes a few microseconds. And at that moment, you need to the mechanical switch, as well as the semiconductor, should be able to withstand the voltage at that moment. The voltage will rise very quickly, so it doesn't give you much time for further opening. So at that moment, you should have a gap between your contact, between your mechanical switch contacts, that's able to withstand the voltage. So if we look at what's happening over there in terms of current and voltage, we notice that we can divide this whole process into a few stages. So, for example, the fault happens at T0, it continues increasing the current, full current continues increasing. At T1, you detect that and you decided to interrupt the circuit. So first of all, you turn off, you somehow, if you have an auxiliary breaker like I showed here, auxiliary breaker, you want to turn off that first, and then the current is transferred to the main breaker, which is this path. Then your mechanical switch should be on the way to open, on the way to achieve a sufficient gap between the contacts. So that would be in the period from T2 to T3. At T3, you turn off the semiconductor, the main breaker, the high voltage semiconductor. So the voltage will very quickly increase to a high value, to a high level in a few microseconds. So at that moment, your mechanical switch should be able to withstand that voltage. Otherwise, there will be a pre-strike. Otherwise, there will be an arc and you fail. So, and after that, what happens? After after that, the current will flow into the MOV. The MOV clamps the voltage, and this clamped voltage, sometimes called the residual voltage of the MOV. That voltage will try to bring the line current down to 0 to finish the rest of the job. So there are a few, I have named each of the period, the time. First, that's the commutation time here, and then that's the mechanical operation time, and there will be a main breaker turn-off time. There will be de-energizing time, which is the time the MOV works. So this de-energization time is very special and is very important for DC switching, because typically in AC system you try to interrupt the circuit at current 0. So the problem is there will be some energy in the line, but it's not as severe as in the DC system. And we have this 1 minute. Okay, let's look at the total time for the interruption, for this DC interruption. We have observed that the commutation time and the main breaker turn-off time basically is very small compared to the other two components. So we say the total time is approximately the mechanical operation time plus the de-energization time. And the de-energization time, I denote as the TMOV, is a function of the residual voltage, the inductance of the system, and the current level. We take an example here. Let's say we have a 10 kilovolt DC system, and the residual voltage of the MOV is 30 kilovolts, and you want to turn off 1,000 amp over there, and you have inductance, total system inductance of 20 millihenry. By calculation, this period of time is 1 millisecond. Then consider we have 1 millisecond mechanical switch. That will be 2 milliseconds. So that's the total time. Okay, it is the TMOV is a function of the voltage, the residual voltage, also the current and the system inductance. So those two, the current and the inductance, is kind of system parameters. Perhaps from circuit breaker design point of view, you cannot change them. But you can change, you can make the residual voltage higher. And that has something to do with the speed of the mechanical switch. So that means the faster your mechanical switch is, the shorter time you'll need to interrupt this DC circuit. Then yes?
You made a statement that there was less energy in the DC system.
I didn't.
Okay.
I didn't. I think it should be more.
Could you repeat the question, please?
Yes. Professor Hopkins asked whether I made a statement that there will be less energy stored in a DC system. I think the answer is no.
Is there more in the AC system?
I think it really varies. It depends on the system parameter, but basically I would assume for a comparable transmission line, there's more energy in the DC system at the moment of interruption than that of the AC system. So yes, then we talk about this fast mechanical switch. This is our target. We try to open the mechanical switch to a certain gap in 1 millisecond, and that should include the opening delay. So we are talking about the total time for this mechanical operation. And we are targeting medium voltage level, so we're thinking about 15 to 30 kilovolts or higher. Considering vacuum, we're using vacuum as the dielectric, so considering that 20 kilovolts equals 1 millimeter in vacuum. And we are talking about 0.7 to 1.5 millimeter in vacuum. We need to achieve that in 1 millisecond, including the opening delay. And we're targeting 630 amps. That's approximately 1 kilovolt payload for this operation, for this mechanical operation. And please keep in mind that in conventional mechanical circuit breakers, it takes 20 to 40 milliseconds for the opening delay, and another 20 to 60 milliseconds for the arcing. So we have a few options to achieve this goal, but we eventually we have a spring mechanism, we have hydraulic mechanism, we have permanent magnetic actuator. Those are actually used in circuit breakers today. Those are available in the market. But spring mechanism, hydraulic, basically mechanical mechanisms, and it involves a lot of moving parts, very sophisticated mechanical design. But the real drawback of the design is actually too many moving parts. And that makes the thing very slow. Then there's a permanent magnetic actuator, which is a newer design, primarily used in medium voltage level vacuum circuit breakers. It has reduced the moving part significantly, but still, because of the operation principle, it's kind of slow. And there are Thomson coil actuators. This is the actuator we are trying to optimize and is used in our design. And there's also something called a piezoelectric actuator. So we have a partner team led by Dr. Stura at Florida State. They are working on a mechanical switch based on piezoelectric actuator. So potentially also has the capability to operate in about 1 millisecond. So how about this Thomson coil actuator and the permanent magnetic actuator? I have made a comparison here. Before that, let's look at how does it work. So basically, Thomson coil actuator is based on repulsion force. So we all played with the magnets. We know sometimes they attract each other, sometimes repel each other away, depending on the poles, the position, I mean. Okay, but Thomson coil is basically based on the repulsive force, and the permanent magnetic actuator most likely is based on the attraction force. So then we know that from my experience, I mean, okay, you have two magnets. When do you feel that the force is the greatest? Apparently, it's that when they are closest. So you really want to put them close to get a larger force. However, if you want them to attract each other, you have to put them far away so they can attract, so they can move, so they can transform these movements to the actuator and to the circuit breaker. But the Thomson coil is based on repulsion force, so you can put them very close at the beginning, and then the force is larger, so you have faster acceleration. So that's one of the key differences between them. All right, I summarized that difference. I think the Thomson coil has shorter energization time. That has nothing to do with this. That has something to do with our coil design. And a larger initial force because of what I explained, and it allows longer travel and also has a faster response. So we plan to pursue this Thomson coil actuator. This is the actuator itself. On the right, that's the actuator itself. On the left, that's the diagram of the whole mechanical switch. So look at this actuator first. The thing we want to do is very simple. We want to dump some energy into the coil. And what happens then is the current flow in that coil, a really huge, fast rising current into that coil will create a large magnetic field penetrating this whole, we call this disk, penetrating this disk. And because it has a faster rising rate, it will induce some current in this disk. And the induced current will react against the original magnetic field caused by the coil. So the easier way to think is that the induced current has a tendency to reduce the magnetic field in it. So, and the easy way is just to run away. So that's how this repulsive force comes from. Okay, we have this Thomson coil, and we need some circuit to drive it, and we need to translate this movement to the contact. We use the vacuum interrupter here as the dielectric and also as the contact. The contact sits inside the vacuum interrupter in the vacuum environment, and there's a shaft connecting this moving part, connecting the movable contact, our actuator, and also some mechanism here. This mechanism is used for damping and holding the movable contact in the open and the closed position. So we have a very simplified mechanical design. We have reduced the moving part, especially compared to the mechanical ones. They have hundreds of moving parts. And in the permanent magnets, they have a few tens of them. In our design, if you exclude those bolts and nuts, those minor fasteners, we have about 10 or less than 10 moving parts. All right, we have this idea. We need to come to a solid understanding of what's really going on there. We started by the multiphysics finite element modeling. What do we have here if we look at this mechanical switch? What do we have here is of course, we have some circuits. We have very complex electromagnetics going on there, and we have mechanical movement, and we want to implement all those into a single model. We will need electric circuit, electromagnetic field, the structural mechanics, and the temperature. So we did this in console. Console is very good for multiphysics simulation. This will be what our actuator looks like. We implement the modeling. We included all those physics in the model, and we can run a transient simulation. So by transient, I mean we can simulate from the moment we trigger the drive circuit for the coil, and then we can calculate at each moment what exactly is the displacement, what's going on in each of the components. On the right, we have seen some simulation results here. For example, this curve, this purple curve, let's say that's the force. That is the force on the moving part, the total force. We are able to calculate that. And that's in a range of 40 kilonewtons here. In a very short of time, but a very high magnitude. And this high peak force will accelerate the moving part and will drive it. So eventually we can open the contact. And we also can capture the current here. So the current here is, in this example, that's 8 kilo amp. There's a lot of current. So you really need to find a good semiconductor switch to control the current. And also we have displacement at each point of the structure. For example, here we can capture the displacement at this point or at this point for the average. So, And here I can show you a short animation of the model. So it's shaking a little bit, but let's focus on this moving part. So what we have observed is that this edge of the disk, for example, first of all, this is actually symmetrical structure. So yes, this should rotate and give you a 3D view. Okay, this edge does not move at the same speed as in the center. It's actually bending. It's bending up and down, and it has a frequency of the bending. So that's something we didn't expect at the beginning, and that is something very important because that actually shows there's just too much mechanical force over there, and potentially it can cause problems. So we need to carefully examine those, including the mechanical stresses in the structure, to make sure that our design is good, is reliable. And we did that. We actually did a lot of, all right, okay. With this simulation, we have a lot of parameters to decide. The design variables, there are a lot of them, and so it's really complex for us to achieve optimal design. But we have, we can change a lot of things. We can change the drive circuit topology. We can change the voltage, the frequency, the geometry of the coils, of the disk, and the whole structure, and things like that. And we can also select different capacitors. We can use different vacuum interrupters. We can implement different mechanical structure for the damping and holding purpose. And we can use different materials. So this is really a complex problem. But let's look at a single parameter. How does one single parameter affect the total performance and our simulation? So we can easily simulate that we can change the voltage of the capacitor bank. We can change it from 200 to 1,400 volts. And what we see is that in terms of force, it increased from tens of kilonewton to that's about 180 kilonewton. So you can easily get ideas of what you are trying to do when you change the voltage. So you really need to be cautious because, okay, you're thinking more voltage is good, more energy is good, but on the other hand, you are putting too much force on your structure. So you want to make it faster, but you also want to make it reliable. So you cannot go too far into it. This simulation gives us some information about where is the limit. So that's just an example, and we have done lots of simulation like this. Eventually, we came up with a structure design like this. So that's the vacuum interrupter. Here is some insulating coupler which connected the metal shaft and the movable contacts. We want to isolate them. And we have two coils, one sitting in this container and one in this container, and the disk sits in between. And we also have a disk spring for the holding and damping purpose. And we have our prototype like this. So in overall, it has a diameter of 8 inches, a height of 14 inches. It's rated for 630 amps, 15 kilovolts and above. Then it's time for us to test it. Our target for the whole purpose we built this mechanical switch is fast operation and low loss. So let's test the speed. This is speed. So at time 0, that's when we send the trick signal to the gate to the driving circuit. We have observed a 1.6 millimeter gap at 1 millisecond, which translates to 32 kilovolts. We have observed a 3.6 millimeter gap at 2 millimeter, which translates to 72 kilovolts. And we believe that even faster speed can be achieved. We just didn't, there are a lot of things going on there, so, but we believe that faster speed can be achieved on our prototype. And we also calculated the voltage drop of the contacts when they are closed. So we inject some current. We measure the voltage drop at 300 amps. The voltage drop is about 50 millivolts. We're talking about a millivolt at hundreds of amps. So it's totally different from semiconductors. And the contact resistance is about 172 micro ohm. And we believe that this value can be adjusted, and we did so. We did adjust it to the value. We can make it down by adjusting the mechanical structure. Okay, and after that, we come back to our finite element simulation. We have compared the measured current, the measured displacement to the simulation. Okay, the dotted lines are the simulated result, and the solid lines are the measured result. So from my point of view, they look like the same. So I'll say our modeling works pretty well. Then it comes to reliability. We are developing a protection device, so it's really important that they work reliably. We have done some repetitive opening and closing operations. For example, here shows 10 times of opening operation, 10 times. And here shows 10 times of closing operation. The 10 times opening operation, it occurs to me that they are also only one. So I think the opening is very good. But look at the closing. The closing is not as good as the opening, and one reason is that the speed is somehow slower, and we did that. We designed that on purpose. We hope that close is slower. Okay. Someone asked a very interesting question about this result. The question is, you tested for 10 times. Does this curve move to one direction? I think that's a really good question. And I come back, looked up my results. I have good record of the result. I know which curve has happened, at which moment. When we found that it didn't go to one direction, and it was even better. It is concentrating, it is converging to the center. That's what we observed. All right. Okay, we have that 1 millisecond mechanical switch, and then we want to build this hybrid circuit breaker. This is our topology. We have the fast mechanical switch here. We have auxiliary breaker here, and we use the silicon carbide ETO in the bridge topology. We also put a capacitor here because we think that the capacitor can greatly enhance the turn-off capability of the silicon carbide device, but it does not really affect its overall operation time. And we tested that ETO, the silicon carbide device, separately. It can turn off 225 amp at 7 kilovolts. I don't have a picture here, but the device is pretty small. It is a 1 square centimeter device. So it is not like a disc type silicon thyristor device. It is silicon carbide, a very small device, and it can turn off 225 amps. We also tested this hybrid circuit breaker. We tested on the relatively low current, 24 amp, but we have a transient recovery voltage at 3.5 kilovolts. It's a pure inductive circuit interruption. There's only inductor in that circuit to interrupt. So that's a pretty pretty close to the real application of DC circuit breakers. And the total interruption time is 1.4 milliseconds. Okay, we have this 1 millisecond mechanical switch, and based on that, I think we can develop a 2 millisecond hybrid circuit breaker. And with this hybrid circuit breaker, we can do DC switching, no problem. But can we do AC? Okay, 2 milliseconds, what does that mean to an AC system? Say 60 hertz AC system, one cycle is 16 milliseconds. So 2 milliseconds is actually a small fraction of it. So at the time the hybrid circuit breaker work, the circuit is actually considered as DC. So it does not matter for this fast hybrid circuit breaker if it is an AC system or DC system. But I think that I'm sorry, the video is interrupted.
You just move the mouse here.
No connection. It's connection.
Everything seems fine. Oh, I see.
Yeah, we've lost connection, so let's see.
Yeah. So yeah, I think they can see the desktop, but
Can you all see? Okay, can you all see the desktop online?
They can see, but
Yes, we can.
Okay, so the audience.
I'll come in and help. You can finish. You can keep going, I think.
Sorry.
Sorry.
To continue.
Yes, let's continue. Mm-hmm. Let me just try. You go ahead, and I'll keep.
All right.
Trying to.
All right.
Oh, I'm sorry.
All right, so we were talking about the AC applications for these hybrid circuit breakers. And we believe that this hybrid circuit breaker should work in an AC system and should work even better than conventional AC circuit breakers. And I'll explain why. First of all, you can do full current limiting, no problem. Okay, it's back. Yeah. Right. First of all, we can do full current limiting, and we can do synchronous switching, and we can use it as the generator circuit breaker. We can use it as a motor starter, and we can also use it as a load tap changer. Those are all conventional like AC applications. First, let's look at what's going on in a case similar to a generator short circuit. This is what happens in the generator short circuit. So there will be a really high DC component superimposed on the AC fault current. If we zoom in this part, we'll see something like this. So we observe that for this period of time, there's no current zero. If you put the AC circuit breaker there, it does not work for this period of time. But if you use the hybrid circuit breaker, it works pretty well. It works very fast. It does not care whether there is current zero or not. So it will be very good candidate for this generator protection. And also there are similar applications. Basically, those are high X over R applications with delayed current zeros. They have similar scenario like this. And something called synchronous switching, sometimes also called controlled switching. So in AC system, when you switch on and off an equipment, for example, a reactor, a capacitor bank, or a transformer, or even a transmission line, you actually want to switch the circuit at some exact moment. You want to reduce the transient caused by the switching operation. I'll give you an example here. So I did a simulation here. It's in face-to-face short circuits, a similar simulation as before, but I put some current chopping level on the circuit breaker. Current chopping in AC circuit breakers means it does not actually wait for the real current zero to interrupt that arm. It has a tendency that at a very close moment to the current zero, it will interrupt. Okay, let's say a typical value would be about 10 amps. So the current is oscillating. When it comes to zero, but not zero at the 10 amp, it interrupts the circuit. So that's not a good thing because at that moment, the system has a lot of energy, still has a lot of energy. And what happens here is, okay, this is the current and this is the voltage. We see two very huge voltage spikes here, which is caused by this. That's just an example of why we need exact control of switching in AC system. With hybrid circuit breaker, with the hybrid solid state circuit breaker, you use the solid state switch to control the switching. That takes a few microseconds. So you can control exactly which moment. And okay, and also I forgot to mention that in conventional AC circuit breakers, they are trying to do this. They are trying to do this using mechanical circuit breakers, as I mentioned, which has a long opening delay, a long arcing time, but they're trying to control as precisely as they can. But the state of art is there will be 2 millisecond deviation. And I would say, okay, we are using hybrid solid state circuit breakers, and the deviation is virtually 0 millisecond. Okay, and I think there will be other benefits for AC systems. For example, the current limiting. All right, so I will not go into each of those AC applications. But to summarize this presentation, we have designed a 15 kilovolt and above 630 amps, 1 millisecond mechanical switch. We have designed, modeled, optimized the Thomson coil for this mechanical switch. We have validated our finite element model. We have achieved 32 kilovolt at 1 millisecond, 32 kilovolt at 2 milliseconds, and we can achieve faster speed. And based on that, we have developed a 2 millisecond DC circuit breaker in which the total operation time actually depends on the system parameter. And we also identified that the solid state is still the bottleneck for this application in terms of voltage and current capability. We also reviewed some AC applications. We think that hybrid circuit breakers can bring a lot of advantage to AC applications as well. We have some publications on this, some journal, some APEC and ECCE publications. We have invention disclosures on the mechanical switch and on DC circuit breaker technologies. And I think there are a lot of challenges and a lot of future work we need to accomplish. First of all, we need to achieve even faster speed. By faster, I mean we need even more powerful acceleration for heavier load, for longer travel. And those can also be used in general linear actuator applications. Based on this, we will be able to evaluate other hybrid circuit breakers. And one real challenge here is, okay, we have a really fast circuit breaker, but is the system able to handle this? So that's really a big question. I've been asked about this question a lot, and I have asked a lot of power system guys for this question. So still, there are a lot of work to figure out how does the AC system take a 2 millisecond circuit breaker. Okay, with that, I would like to thank the University of North Carolina Coastal Study Institute, who sponsored my work, and the National Science Foundation for supporting our work. I would like to thank my advisors, Dr. Alex Fong, Dr. Iqbal Hossain, my mentors, Dr. Bruno Lequin, Mr. Roger Briggs, and my colleagues, especially Mr. Yang Chu, Mr. Xiaoqing Song, and Chris Sample. Thank you.
Thank you so much for the presentation today. We have just a couple of minutes to take some questions. So let's go first on the line and see